So we have to also keep in mind and a good balance sheet for average heat capacities. The heat capacities are evaluated. Heat capacities are strong functions of temperature. And they are given in functional forms as such. So it may not be very convenient to deal with those heat capacities with complex equations that we have to deal with for material and energy balances in a chemical reactor. Instead, we may have to use an average value for those heat capacities that is averaged sometimes precisely for the temperature range that we are interested, or for a particular range of temperature. The concept of averaging means that finding a number that best represents the function in the given range. In other words, the mathematical representation of this, I'm going to use double bracket to represent that this is an average quantity. This is going to be an integral between an initial and final temperature, a temperature range of interest to us, this function, integrated over temperature, divided by the temperature. Now this mathematical operation is equivalent of the following graph, following diagram. Suppose that you have plotted the heat capacity as a function of temperature, and this is your function. By integrating between T0 and the final temperature T, you are estimating the area under this curve. Dividing it by the temperature difference means T minus T0. The average heat capacity in this diagram corresponds to a value that is going to give us the same area cutting above and below. The losses are compensated by the gains, so that this number is going to be valid throughout instead of having a precise value for each temperature. And hence our analysis is simplified. This is one of the heat capacity averages. Okay? So this heat capacity has to be evaluated for each species. Now then, the next average heat capacity is for the mass average heat capacity for the mixtures. On this side of the problem, we're going to have a weighted average. Heat capacities. This weighted average heat capacities are going to depend on the fraction of the component in a mixture, and we are going to make the assumption that upon mixing there are no non-idealities. In other words, as a result of mixing, no endothermic, exothermic events have taken place. So, if there are no non-idealities upon mixing, the mixture total enthalpy should be a net summation of the enthalpy contribution coming from each of the species. Na times H sub A, Nb times H sub B, and C times H sub C. And enthalpy, as such, is represented in terms of the heat capacity multiplied by the temperature minus an arbitrary reference temperature. Now, if we substitute this expression for enthalpy for each and every one of those terms, the equation takes the following form. Those terms are common for all species, and we cancel them out. And if we divide both sides by the N total, we get the average heat capacity. I will indicate with an overbar as YA times CPA plus YB times CPB plus YC times CPC. CP average, so let's write it here also. We had a mixture mole fraction, mixture mole feed mole ratio term used in our analysis. So I will also leave that form of the average heat capacity as well. Here, theta I is the ratio relative to a reference component. Now, the rules for the heat capacities also are valid for the constituents of the heat capacity functions if the functions are of the same form. If all of the functions are of A times T plus B times T squared plus C times T cubed, you can apply the mixing rules for A, B, and C as well.